Hello my friends, and welcome to another Seismic video working through the AQA Physics Paper 2 topics, and this time we are going to be looking at waves. And in waves we need to consider difference between two types, which are transverse and longitudinal. We're going to look at the properties of waves. We're going to look at examples of mainly longitudinal ones in the form of sound, ultrasound and seismic waves, which can be both transverse and longitudinal. We'll look at electromagnetic waves, the specific examples of different groups. We'll look at how they behave a little bit. If you're doing physics, the separate science course, not combined science, you'll look at lenses and how they work and how to draw diagrams, and also something just on the add-on at the end, something called black body radiation. So let's start by defining a wave. And a wave is something that carries energy. It carries energy from one place to another without transferring matter. So energy is carrying from place to place, but the matter itself is not travelling. So with a seismic wave from an earthquake, from a centre of a seismic shift, the material is not travelling from the origin to where it's felt, it's just the wave of energy. So it's oscillations in that physical material that's travelling through the ground to be then felt. As far as electromagnetic waves go, coming from the sun, it's not matter that's coming from the sun to the earth, it's just energy. So waves carry energy from one place to another without transferring matter. And the two examples we have are transverse and longitudinal. And the key difference is in the direction of the oscillations compared to the direction of the energy transfer. So for a transverse, trans means going against, and in this case oscillations are going against the normal direction. So they are actually, the word we use is perpendicular. And you get common questions where you have to compare transverse and longitudinal. So the oscillations in transverse are perpendicular to the direction of the energy transfer, which is in this case going to the right, whereas the oscillations are going up and down. So oscillating completely 90 degrees to the direction of the energy transfer, or the wave. Whereas for a longitudinal wave, the oscillations in this case are parallel. And that's another key word. So they are parallel to the direction of the energy transfer. So the oscillations in this case are going forwards and backwards, and a particle's just literally going forwards and backwards like that. And that's causing this wave of energy to pass to the right. It's going this way. And you find these little compressions and rarefactions. So this is a compression. If you imagine this is a slinky, I've got an email. This is a compression, and this part at the bottom is a rarefaction. We're going to label the transverse diagram in a moment on a bit of a better diagram, but that's the difference between the two. Examples of them: transverse, you'd find them as electromagnetic waves. They're the big examples, so light, microwaves, radio waves, that sort of thing. And in longitudinal, sound is a really good example. Sound is a perfect one, and seismic waves can be both longitudinal and transverse. So this is an example of a diagram which is seemingly representing a transverse wave, but this could be measuring the change in amplitude of a longitudinal wave too. So we can convert sound waves to look like this if we receive them. It's just the same, it's just a different way of representing it. However, we can recognize on this two of our very important keywords regarding waves. One is amplitude and the other is wavelength. And amplitude here is just the distance of the oscillation from the origin, from zero. So if this middle line running through the middle here is 0, amplitude is how far at the maximum it has travelled from that 0. So above or below, those amplitudes should be exactly the same if this is a normal wave just travelling the same rate all the time. And so you could take a reading from this graph, you could find out how much that is, 10 whatever units it might be. The wavelength, however, we can measure in a slightly different way. So the wavelength is the length of one wave. I mean, that's the key word itself, that's pretty obvious, isn't it? But how do we measure it from this graph? Well, you could measure it from many different locations, as long as you have a whole positive side to the wave and a whole negative side to the wave. So if you're starting at the peak, you have to measure to the next peak, and you could track that distance between those 2 points. You could do it from the bottom of a trough to another bottom of a trough. You could do it from after a positive bit to another after another positive bit, as long as it's measuring a whole wave. If any of those are tracking a whole wave, you could do it from part way down if you wanted to, as long as you end at the same point on the next part of the wave. As long as you're taking that measurement, that's the wavelength, and that is when the units here are in meters, or a measure of distance along that x-axis. If, however, the unit is not in meters or distance, it is instead in time, we get a different set of data from this graph, because we instead can see how long it takes for one wave to pass a start point and complete its journey. And that tells us, for example, if it's 1.5 seconds to do that part of a journey, that tells us the period of this wave. The period is the time period it takes for one wave to pass a point. And if we can calculate that period from our graph, we can then use an equation that we're given to work out the frequency. And the equation we need for this is one we are given. So it's given to us, and it's t equals 1 over f, or in word form at least. And that's where t, which is what we've just worked out, so that's our t, 1.5 seconds, is equal to a constant of 1, because it's about kind of inverting this, divided by frequency. So we're trying to turn the time it takes for one wave into the time, into the number of waves passing every single second. That's what the frequency is. So frequency is measured in hertz, and this is a measure of how many waves are passing a point every single second. So here we would have rearrange our equation, so swapping the f and the t, gives us f equals 1 over t. And that is equal to 1 divided by 1.5. And of course I could have chosen a much easier set of numbers to work with, but 0.666666 reoccurring hertz, or 0.667 waves passing a point every second. That's the frequency of this wave. The other equation that we need to know that fits with this, though, is one that we actually need to be able to recall, is one that ties together wavelength, frequency, and something called wave speed, which you'll go on to have to be able to work out. And that's where we have wave speed as v equals f times by lambda, which is the symbol for wavelength, which is usually measured in meters. Time period was t, measured in seconds, and frequency is, f is a symbol measured in hertz. And this equation just gives us exactly the wave speed. So frequency hertz, wavelength in meters. Technically hertz is per second, so we're multiplying meters by per second, and it gives us meters per second. That's one you have to recall and use. So let's look at 2 required practicals that you should have done, where we have to analyse and talk about the methods and think about how we could measure wave speed. So if these are set up to measure wave speed, you need to calculate v from f and lambda. You might want to rearrange that to lambda f. Doesn't really matter. In fact, in the exam, you could write this however you wanted. You could do lambda equals v over f if you wanted to instead. They will credit you just the same as long as you've arranged it in a way which is actually technically correct. But the standard way is v equals lambda f. Now, to get lambda and f, we need to take some different readings. So you have to use a ripple tank, or you can measure it from on a string. There are other methods that you could use that they could bring up which are kind of context, so you have to consider what measurements you still have to take. But these are the 2 that we need to know the methodology for and how to use the data. So for a ripple tank has the vibration plate at one end of a layer of water, and that will ripple up and down, causing waves of water to travel along the tank. And so what we can do is we can take a picture of the top of the actual waves, and then we can actually measure a set distance. So we could measure from this wave all the way to the end to this wave and count how many wave fronts there are, and divide by how many there are, and divide the length by how many there are to work out the length of one wave. And that length of one wave will give us our wavelength. So let's say we've got here 1, 2, 3, 4, 5, 6, 7. That's a really weird way of counting it. We have 7, and let's say it's a distance of 70 centimeters. It gives us a wavelength of 10 centimeters. Now wavelength should really be in meters, so I'll convert that into meters. Job done. The other thing that we need is our frequency. So to get our frequency, we need to actually watch this in real time, and you could count for a number of seconds. So you could count for a number of seconds, or you could set a count of how many waves you want to pass a point, but try and get a reading of how many waves are passing a point every single second. So let's say we've got, we're counting for 30 seconds, and we know that, I don't know, 15 waves are passed. And if we then do 15 divided by 30, we can find out that we have 0.5 waves passing a second, which is 0.5 hertz. So with that, we then have V equals 0.1 times by 0.5 equals 0.05 meters per second. Sorted. That's our wave speed. Measuring it on a string, we have to have a slightly more intricate little setup. So for this, we have to have our vibration generator. This here is our vibration generator, which is oscillating up and down, and we have a signal generator, SIGGEN, which is linked to that. And the signal generator will basically tell the vibration generator how regularly to go up and down and by what amplitude. So what we tend to do is we tend to fix the frequency on this. So we have the frequency predetermined on our signal generator, and what we can do is we can adjust the wavelength here until we get a standing wave. So this here is a movable bridge, and that movable bridge can be moved forwards or backwards, away from or towards the vibration generator to create a standing wave, which is where it appears that the string is stationary. If you put it in the wrong place, you'll just see that basically the string doesn't have any clear pattern to it. We want to be able to see one whole wave, so you need to basically get it to the point at which you're demonstrating one whole wavelength or two wavelengths, but set up in a way that it will perfectly make the pattern that we can measure. What you can then do from that is you've worked out the wavelength. So if you can see one whole wave, there is your wavelength. You'd measure this distance. If you could see two wavelengths like this, then you would measure the length of the two waves, halve it to get one wavelength. But as a result of that, you've got your lambda. And if you've got those two readings, once again, V equals lambda F, multiply them together, you've got your answer. In the 2019 GCSE paper, they were asking you to discuss how you could investigate the effect of changing the tension in this string, how it would affect wave speed. And it was a cheeky little question quite early on in the paper. So you'd put more or less masses on here. You want to do a number of those so that you can investigate a trend, so 3 or more. Every time you change the mass, if you're keeping the frequency the same, you'd have to adjust where this moving bridge is by moving it away or towards to increase or decrease the length of the string so that you can see a standing wave. And if you're going to increase the mass that's on this, the tension, if you like, by adding more mass, it's going to lead to the velocity of the wave increasing because the string is going to be more taut. And because we're keeping the frequency constant, the wavelength is going to decrease. So what you'd have to do is then actually move the wavelength, not the wavelength, the movable bridge closer to the vibration generator. And they will be looking for that distinction in this paper. They were looking for you to be correct about the direction that was going to have to be moved to get the top marks, to get that grade 9. But it's a good little practical. So when we get to looking at electromagnetic waves, we need to be using some keywords, and this is a physics only, it's not a combined science set of keywords, but it's worth knowing them anyway because they are very relevant. And they're simple really. If something is absorbed, it's going to hit the surface, and the energy is going to be absorbed by that surface and not be released anywhere else at that moment. If it's transmitted, it is able to pass through the material. So windows, for example, will transmit most of visible light. And if it's reflected, it's going to hit the surface and then bounce back. And it's going to follow a really important rule where the angle of incidence is equal to the angle of reflection. So it's going to bounce off at the same angle. The other word that we will look at is radiation, which is where some energy is being radiated out from a surface, and that usually happens when it's absorbed. infrared radiation, for example, is absorbed, and then it's radiated back again in all directions from where the object is. So just to unpick some examples of different types of wave, this is sound waves, which is a physics only, so not combined science and higher tier only concept. There's not much to know really, but sound waves are longitudinal waves, so they are vibrations, collisions of oscillations of particles that cause a transfer of energy but not matter, and they will travel through solids, liquids and gases. It's literally one particle colliding with another particle. As it does so, it will transfer its energy to it, which will then move to the transfer energy even more. So it needs particles to be present, so it won't travel through a vacuum, for example, in space. So the way that we can hear is through using an eardrum, and that works just in the same way. It needs to have particles colliding with it to pass energy on. So what we have happen is we have the sound hitting particles in the gas and the air around us, and those vibrations in the air will hit our eardrum. And those vibrations of our eardrum will cause tiny little bones in our ear to then cause the vibration of another kind of membrane, which will cause vibrations in a liquid in our inner ear called the cochlea, or ear snail, some people so well describe it, and it causes little sensitive hairs to pick up the vibrations, and the vibrations felt will depend on the frequency of the wave, which will cause different depths of that cochlea to be activated, if you like. Your brain then deciphers it. But our ears are capable of hearing a range of 20 Hertz to 20,000 Hertz, so we are quite diverse in the range of sounds that we can hear, but obviously they're very different to different animals. So dogs are very different to what whales can hear, to what bats can hear, completely different set of ranges which we can hear. But you do need to know those numbers: 20 Hertz to 20,000 Hertz, 20 Hertz to 20 kilohertz. And beyond sound, we have ultrasound. Ultrasound meaning much higher frequency than our own hearing, basically just outside of our range, above what we can hear. So ultrasound machines that are generating ultrasound are generating a sound wave, but it's so high in frequency, that we can't hear it. So let's explore these a little bit more. So waves will have differences in velocity. So this is a physics and higher tier topic only, they will have differences in velocity and absorption and reflection in different media or mediums. So media basically are different materials, so be it in air or in liquid or in bone, in blood compared to tissue fluid, compared to muscle tissue, compared to fat tissue. It will cause a difference in velocity. And the reason I bring up these different types of tissues is because ultrasound is commonly used in a medical type of imaging. It's also used in industry for examining defects in materials and in metals and things like that. But they're most commonly thought of as being used in medicine. So they have a high frequency, and what happens and why they're useful is because when they hit a boundary between media, so let's say between skin and between tissue fluid, or between amniotic fluid and a baby's skin, we have a partial reflection. So that means some of the waves are reflected, but not all of them. And the time it takes for the reflections to reach the detector shows us how far away the boundary is. So we've got the ultrasound generator is generating waves. These waves will go and hit a boundary and then come back to that generator, which also has a detector. So it's measuring how long it takes for the wave to be sent and come back again. So if it's taken 2 seconds, well, that's a vast over exaggeration. If it's taken 0.2 seconds, which is still very slow, to be sent and come back, that means it's only actually taken 0.1 seconds to get to the distance away. Now, we know how fast these waves will travel, approximately. Well, actually, no, forget that. Very accurately. We know how fast they're travelling, and we know the time it's taken for them to reach the surface, the thing that's bounced off. And so therefore we can work out the distance because of the equation distance equals speed times time. And so we can use that equation to work out how far away these this object, this boundary is. And because we have partial reflections, we can collect a lot of data from this one set of ultrasound that's being sent out. And so we can generate a picture of all these different surfaces that the sound waves are travelling through, how far away they are, and how strong a boundary it is. And so we can start detecting how big an object is, how big a child developing baby is, how big a tumour potentially is, gallstones, a defect in a pipe. Whatever it is, we can detect it using ultrasound, and it's a very smart and very cheap way of identifying problems. The other type of wave, on the other hand, is a seismic wave, and seismic waves are both longitudinal and transverse. And so primary waves are the first type of wave, and secondary waves arrive secondarily afterwards, after a primary wave, from an origin of like a seismic shift or something like that. And so a primary wave is longitudinal, and these will travel through both solids and liquids. Now, a secondary wave is transverse, and these will only travel through liquids. And the reason for that, hang on, that's a mistake. That's a big mistake. They will travel through just solids. But the reasons for that is, if you think about how the oscillations work, the oscillations for a longitudinal wave are forwards and backwards. So if you've got a solid where the particles are linked together, if they are moving this particle, it's going to be moving this particle too, because they are in effect linked through intermolecular forces. If it's a liquid, they're not going to be linked. However, that particle is on the left is still going to be colliding with the particle on the right, and so passing the oscillation forwards. In a transverse oscillation, though, the oscillation is perpendicular to the direction of energy transfer. So this particle is going to be moving up and down. Now in a solid, those two particles are linked together through intermolecular forces. So if the particle on the left is raised up, it's likely that the one that's on the right is going to also be pulled up too. However, in a liquid, this is why I clearly made a mistake, in a liquid, particle on the left is going to get raised up with this oscillation. That movement, that energy, if you like, is not going to be passed on to the one on the right, because they are not linked. So that oscillation is not going to be passed on. So transverse waves will only travel through solids where there is that link, that intermolecular force linking the two together, so that it's carried away as well. And the reason that's been useful for us is that when we look at the Earth and we look at an earthquake, which is this red dot, we can actually pick up the seismic activity, the movement in the Earth, from that earthquake at different points across the world where we have sensors. And what we found was, on the other side of the world, we're not picking up any S waves at all. We're only picking up the P waves. And that tells us that somewhere in the middle of the Earth, or it told us that somewhere in the middle of the Earth, in the core, there is liquid, because these waves can't travel through liquids, so there must be liquid in the core of the Earth. And based on how far down around the Earth we could sense these S waves as well as the P waves, we could work out how deep that core was. And so we found out that the inner core is liquid. It's pretty cool. And the final use of this type of wave and ultrasound, using the idea of reflection, if you like, is through echo sounding, which is like the common link to submarines, where you hear boom, boom. It's a great demonstration where we're sending out high frequency sound waves, and we time how long it takes for those sound waves to get pinged back, and we can find out therefore how close the seafloor is, or how close objects below the ship or the submarine are. As far as the examples of electromagnetic waves go, we need to know the full spectrum, and there are 7 categories within the spectrum. Some of them overlap a little bit, but we need to know them as discrete sections, and they're categorized based on their energy levels, their frequency and their wavelength, which all correlate together, and their uses. And the order of them is RMI, V, UV, X-ray, gamma ray, and you can learn a little acronym. There's loads of them around. You can make up your own one if you wanted to. The one I tend to go for, though, is Raging Martians Invade Venus Using X-ray Guns, and it just arranges it this way, and that is according to their frequency and their wavelength. both of which are the inverse of each other. So the radio wave end is a low frequency, but it's a long wavelength. And as you get further along the spectrum, if you go that way, we get a high frequency and a short wavelength. So gamma has the shortest wavelength and the highest frequency, whereas radio waves have very long waves, kilometers long, whereas low frequency. The energy levels, though, are higher at the gamma end than at the radio wave end, and the absorption of those can mean that things like atoms can be ionized. So let's just talk about the uses quickly. So radio waves are obviously used in radio, they're also used in television. Microwaves are used in satellites and also used, as you know, for cooking food. There's a very specific frequency of energy of the wave that will cause water to vibrate and therefore get warmer. Infrared is used for heating, so in heaters cooking. It's also used in infrared cameras. Visible light is obviously used for us to be able to see. It's also used to send information via fiber optic cables. Ultraviolet is used in lamps. It's also used in sun tanning because it causes a reaction in our skin to cause us to be tanned. It can also cause skin cancer, though not so good. X-rays are used in medical imaging, and treatments and gamma rays are kind of the same. X-rays and gamma rays are pretty much the same thing, it just depends how they're created to define them. This little blue margin here is really important because anything this side of, so the right hand side of that line, that margin, is classed as an ionizing radiation. The boundary there between visible and ultraviolet is very small. Some animals, like birds, can see into the ultraviolet spectrum. We can't, but that is very, very close. So the ultraviolet and upwards has enough energy to be ionizing. And so that means that your atoms will lose electrons and therefore become ionized. If that happens to your DNA in your genes, it can lead to mutations, lead to things like cancer. Not good. We'll look at that a little bit later. If you're doing higher tier, I mean, I don't know why this is higher tier especially, but you just need to be aware that different substances can absorb or transmit, which means let it through, can reflect or refract with different EM waves, and this may be due to the different velocity that the wave has in these different substances. Looking at this in a little bit more detail, we need to know that it is the changes in atoms or nuclei that can cause the release of electromagnetic waves. So when you look at the atomic structure or radioactivity topic, you'll look at how the change in the atom structure or the nuclei breaking down can cause the release of some energy in the form of gamma waves. What can also happen is if you have an atom with its electron shells, if one of these electrons in the electron shells gains some energy, these shells are technically energy levels. It can go up an energy level, and once it all kind of calms down a little bit, that energy can be released. It can come back down a different energy level, and that energy can be released as electromagnetic radiation, which is how we generate things like radio waves in transmitters. So you just need to know changes in atoms or nuclei can cause the release of the electromagnetic waves. And we saw earlier, we've got ultraviolet, X-ray and gamma rays are ionizing, and the effects of which depend on the type of radiation. So gamma and X-ray are much higher energy than ultraviolet, and also the size of the dosage, so how many of these packets of energy are hitting the atoms. So if you've got a high dosage of gamma radiation, it's going to potentially do you quite a lot of harm. And this dosage is measured in sieverts or sievert, which is just the unit of dosage. This ultraviolet can cause skin to age prematurely. It also increases the risk of skin cancer, and X-ray and gamma rays can cause a mutation of DNA affecting your genes and therefore leading to potentially getting cancer, which is just where the mitosis mechanism in your cells has gone wrong. And that can sometimes spread around your body, but you know a lot about that from biology. If you're doing higher tier, you need to know that radio waves are just caused by oscillations in electrical circuits. So oscillations in an electrical circuit would be the current. Current's moving forwards and it's moving backwards, and as it's doing that, it's causing radio waves to be created. If you think about an antenna, it has this kind of structure. You have electrons moving around this whole circuit in various loops, and as it does that, it's going to cause basically these oscillations in these wires will cause radio waves to be created. These oscillations hitting another wire somewhere else, hitting a receiver, will then create an electrical circuit, and cause the electrons to start moving in that circuit and therefore be received, and that can be turned into the music that you play for a radio. And it will create an alternating current. So if you've got a receiver, it will create an alternating current with the same frequency as the radio wave itself, because that packet of information that's being sent as a radio wave will cause the same oscillations to be created in the receiver as were created in the transmitter. So the next property of waves that we're going to look at, which leads later into looking at lenses for the physics only part, is the property of refraction. So reflection is where waves will bounce off a material. Refraction is when they will pass through a new medium, but they will have their velocity altered, and as a result of the velocity being changed, they will slightly change direction or significantly change direction depending on the difference in the types of medium. So if you look at this diagram on the right here, we've got these wave fronts arriving at a boundary to a different medium. So here's the boundary. And this could be, for example, waves in deep water arriving into an area that has shallower water, suddenly entering onto a wave-cut platform or something. But these waves, when they're in the deep water, will travel faster, and when they're in the shallow water, they will travel slower. So if you look at this first wave front at point A here, this first wave front has hit the water and hit the shallow water, and where it's hit shallow water, the end of this wave gets slowed down before the rest of the wave does. So the remaining part of the wave continues at its normal velocity, whereas the part that's entered the shallow water has slowed down. As a result of this, it looks like the wave actually changes direction, and it does. And if you do the same with light going through a perspex block, for example, it's going through the air nice and quick, and when that wave front hits at one end, the boundary of this perspex block, that one end of the boundary gets slowed down, and as a result the whole wave front will eventually change direction. And when it then leaves to enter the air again, the part that enters the air first will speed up first and eventually change the whole direction of the wave back to the direction it was going before. The best analogy to try and understand why this happens is if you think of a car that's driving along a road, and it veers off the edge of the road, and it's two wheels. One of the wheels enters a puddle of mud on the left-hand side. That side's going to get slowed down a lot more than the side on the right. This side's going to continue travelling a lot faster than the left side of the car, and as a result, the car's front will basically turn, and that turning is causing it to change its direction, and it will go from going straight forwards to heading off in a direction like this. This is exactly what's happening for these waves, just the wave front is changing direction because it's travelling at a different velocity. What you'll notice though as a result of that is the distance between the troughs or the peaks of the wave, so the wavelength therefore is going to be different in these two locations because the speed has got smaller. And using our wave equation, v equals lambda times by f, wavelength times by frequency, if we're decreasing the velocity, the frequency is actually going to remain the same here, and the wavelength therefore has to decrease. So you can see that the wavelength for B is shorter than the wavelength for A. The frequency is remaining the same, the velocity is decreasing. So if you're studying the physics course, you need to know about lenses and how they behave. This is physics only, not for combined science. And we're going to just define some words first. So lenses basically refract light. They are about refracting light, changing their direction by altering their velocity as they enter a different medium. And there are two types of lenses that we need to be aware of. One is convex and the other is concave. Concave will have the shape of a cave structure like this. And as physicists like to do, we don't like to draw out lenses all the time. As you can see, I can't draw very well. So what we use is we use symbols to represent these lenses. So concave lens is represented by two inwards facing arrows, if you like. And that's what we draw for a concave lens. A convex lens, on the other hand, we draw outwards facing arrows. And convex lens would look like the more traditional lens, like the lens we have in our eye, where it's thicker in the middle than it is at the top or the bottom, and concave is thinner in the middle than it is at the top of the bottom. But both of these lenses will cause light to behave in a different way. So convex lenses will cause parallel rays of light to be brought together to focus at the principal focus, which we'll get to in a second. And they can produce two types of image. They're either real or virtual. And these will depend on the distance of the object from the lens. So the object is what we're trying to see, So if you have your lens drawn, depending on how close your object is to that lens will affect whether it ends up being a real or a virtual image that's produced. A real image can be just defined as an image that can be projected on the screen, whereas a virtual image is one where the object appears to actually be in a different place completely. So when you look at yourself in a mirror, for example, your mirror makes you seem to appear to be behind the mirror, whereas actually you're not there at all. You're actually where you are stood looking at the mirror. So this is creating a virtual image, whereas that real image is being projected onto a screen, perfectly showing its true reality. You can't display a virtual image onto a screen, but for a real image you can. It's a weird concept to try and get around your head, but learning your definitions can sometimes be the way forward. So one of the skills they like to have you demonstrate in this physics topic is how to draw lens diagrams. And you'll be shown something like the diagram below, which if you haven't seen lens diagrams before, might just make no sense to you at all, which is fair enough. It's just a whole bunch of weird lines and arrows. But we can label a few things on this to make a little bit more sense. So we've got our lens here, and we know that this lens is a convex lens because of its diagram that's been given. This here is our object. This is just an arrow, and the object is represented as an arrow because it shows the orientation of the object and also its size. So it's got a magnitude and it's got its direction it's facing to, because we want to know if these objects get inverted or they remain upright, and we also want to know if they get smaller or bigger or remain the same size. So this is a convex lens, we've got our object, and you've also got this extra mark here and here, which is a certain distance away from the lens, and that's a principal focus. Now, different lenses will have different focal lengths, if you like. If you know anything about cameras, they have different focal lengths, and this is the focal length. So the principal point of focus, and this is also the axis, the principal axis, which is running right through the middle of the lens. So you'll be typically given all of this information, and what you'll need to then do is draw how the object will appear once light has travelled through the lens. And so for a convex lens, you need to draw 2 ray lines. You could draw 3, but you only have to draw 2 to get marks, and this is probably the easiest way to do it. And the first line that you want to draw is from the top of the object, directly parallel to the principal axis, which is in the middle, and then down to the focal point. So you're drawing it from the top of the object right to the lens, parallel to this line. And then once you've drawn it to the lens, it needs to then go through the principal focus, through the focal point, going right at the other side. My line there isn't perfect, but you get the idea. The second line that you need to then do is going directly from the top of the object all the way through the center of the lens. And this is really good because you can see that it overlaps at the bottom right hand corner, and this overlap point where these 2 lines intersect is where our image is going to be formed. So that's going to be now the top of the object, so that's going to be our arrowhead, and then it's going to form the object image. If you imagine this is then projected on a screen, it'd be in focus there, projected on the screen, and it would be a larger inverted image. So it's larger and it is inverted. The word we use to describe larger is magnified, and if it was smaller it would be diminished. So in this case, where this object is placed, it's further than the focal point on the left hand side of the lens, and we're getting a larger inverted image as a result. In contrast, for still a convex lens, we have here the diagram label for a convex lens. Here you can see the object is much closer than the focal point, but we follow the same rules, so I'm going to just draw it really loosely this time. You do a parallel line from parallel to the axis, a line going to the lens, and from that line you then go through the focal point, and then again you have going from the top of the object directly through the middle of the lens. But you can see that these lines, they're actually diverging away from each other. They're further away here than they were at this point. And so for this case, what you actually have to do is track them backwards from the lens, find a point at which they then intersect. It's very poorly drawn, and when they intersect, then you actually then draw the image again. But this image is formed on the wrong side of a lens, so we're not able to project it upon a screen. And if you're not able to project it upon a screen, you're creating a virtual image. So this is a virtual image. It is virtual, and it is also much larger than the the original object, so it's magnified, and it is upright. But if we, again, for a convex lens, you could make a diminished image if you wanted to. It can be done. For a concave lens, if you look at this one, you see the diagram representation of the lens is different. This is a concave lens. We have to follow a slightly different method to draw where the image will be formed. So the first line that we have to draw on is going to go from the top of the object to the lens parallel to the principal axis, which is what we've done before, and then down to the focal point in front of the lens. So from this point, we're going to the focal point in front of the lens. What we're then going to do is we're going to do the second line, which is from the top of the object directly through the center of the lens and out the other side. So from the top of the object directly through the center of the lens and then out through the other side, which was terribly drawn. No, here we go, much better. And what we've got then is a point of intersect, which is going to be where our object is formed, which in this case is on the wrong side of a lens, therefore it's virtual, and it is also diminished. It is virtual, and it is upright. But these concave lenses will always produce a virtual image. You'll never get a real image formed, and that's because the way that it works is diverging these light waves all the time. So whenever light travels through this lens, it is getting spread apart. They're never going to intersect on the right side of the lens, if you like. So they're never going to be able to focus on the right hand side of the lens over here. So you're never going to get an image that can be projected upon a screen, and so therefore it's never going to be real. The extra part for visible light, on top of how lenses make light behave, is just generally how they work. So each colour that we have in visible light spectrum has a very narrow band of wavelength and frequency, and again, a bit like when we look at the spectrum, we can categorise these different types of electromagnetic wave, but they do overlap quite a lot. And if you look at the visible light band, again, you've got some reds which are very similar to the pinks, which is quite similar to orange and yellow, and there's overlap of different parts. But we tend to say there are different bands, different areas of them. Now, all of these visible light waves and all of electromagnetic waves can be reflected in two different types of ways. One is specular and the other is diffuse, and it depends on the surface itself. So if you have a specular surface, it tends to be completely flat. And that means that basically any light that hits it is going to bounce off in the same direction in a perfect form. So if you have a reflection of your face, the light hitting your face is going on to hit a mirror, for example, it will reflect your face perfectly back. Whether that's a good thing or not, it's up to you to decide. But diffuse reflection is where the surface is kind of random in shape and structure, and so when you have light hitting your perfect face, it's the light reflecting off your perfect face onto this diffuse structure, diffuse surface. The light will hit it and it will ping off in all kinds of random directions, and so the light that you're then deciphering as it comes back to hit your face and your eyes, you can't then actually detect what image originally hit that surface. A bit like most objects, light is hitting it, that light that's hit that surface coming back to your eyes, so you can detect that there is light coming off that surface, you can see what it is, but you can't see an image being reflected off of it back to you. And diffuse just means basically the rays of light, the waves of light that are hitting it are diffusing off in different directions. Specular is a bit like glasses, I suppose. It's a way of basically explaining that the light is bouncing off it perfectly. The final property that we need to know for visible light in physics is how colour absorbance works, how different objects appear different colours. And if you have a red object, for example, this red object will only reflect off red light, so it must be reflecting all the other types of colour of light. So it's absorbing the green light, it's absorbing pink, orange, blue. The only colour light it's reflecting off is red, and therefore you're receiving red light into your eye, so you see that object as being red. If you look at a plant, most plants look green, and that's because plants don't use green light in photosynthesis. So the chlorophyll in those plant cells are green because they're absorbing the red and the blue ends of the spectrum. The green is not being absorbed, it's being reflected off, hence why it looks green. If you had orange object, it is reflecting off the orange light, it's absorbing all the others. If you have a white surface, that white surface must be reflecting all of the colours of light that's hitting it. So a white surface is very reflective. In contrast, a black surface is going to be absorbing everything. A perfect black surface, a perfect black body, as we'll look at in a second, absorbs all the colours of light, and therefore it's not reflecting any radiation, any visible light radiation back to your eye, so you see it as the absence of light. So to continue that, if we look at black body radiation, which is focused not on visible light but on infrared, we know that all objects emit infrared radiation. That is to say that all objects have energy, and therefore they're all radiating heat, and that's what we understand at least. All objects have energy. We don't know anything that is absolute zero as a temperature. The hotter something is, the more infrared radiation it will radiate. So if you are warmer, you're going to radiate more heat, as you might see in a infrared thermometer, infrared camera. Now, a perfect black body is going to absorb all of the radiation that's incident on it, so all the radiation that's hitting it. And that means there is no transmission and there's no reflection. It's not letting any back out, it's not letting any through, it's absorbing all of it. And that good absorber is also a good emitter. So a perfect black body would also be the best possible emitter, which is a bit of a strange thing. So it's going to absorb all this energy really quickly, but it's also going to radiate that energy out quite quickly. Now, the examples of exam questions so far talking about this idea have talked about the Earth, and how if the Earth is at a constant temperature, this body, which can be any object, is absorbing and emitting radiation at the same rate. Now, with global warming, climate change, for it to change its temperature, it must be absorbing more radiation than it as a body is emitting. And the way that that is happening at the moment is that the increase in greenhouse gases is meaning that less heat is being emitted from the Earth. It's being re-emitted by the Earth, but it's getting trapped by greenhouse gases in the atmosphere. And that's stopping the radiation being lost. And that is it for our specific run through of the physics specification of the topic waves. If you have any questions or queries or comments, please do leave them below, but do like and subscribe. Thank you.